Fong-Jones. I'm joined by Mckaig, and we're both from the Site Reliability Engineering team at Google. So I wanted to give a brief idea of kind of the expertise that we're bringing of how we think about debugging production systems. So I've spent a while at Google. I've spent 10 years at Google, which I'm a little bit embarrassed about. But it's been on 8 different teams, so I've seen a whole wide range of different ways that teams cope with using tooling and process and techniques in order to help their debugging go faster. And right now my day job is I work with the customer reliability engineering team to teach our customers how to do DevOps, how to do SRE. Because at the end of the day, SRE is a way of doing DevOps.
Hi, my name is Mckaig, and I joined Google in the SRE group about 1 year ago. So I'm still relatively new. The reason I'm talking today is when I joined Google, I was kind of blown away that they are operating systems much bigger than anything I've ever touched before. But things go wrong, like at every company, we have production outages. But somehow they were able to solve those outages using tools and techniques which weren't magical, but they were so sophisticated compared to what I'd been using before, they sort of blew me away. So this talk is really aimed somewhat at myself, but 18 months ago, where I'm hoping to share some of the techniques that we will use to solve outages, such that you can adopt them in your own organization. Maybe they can help you too.
So let's talk about some grounding details. Like, what do we assume that you're already doing in order to kind of get the most of these techniques? So we're assuming that you have a service or collection of services, that you have some microservices, and we're assuming that you have maybe like a Kubernetes cluster, or that you're running across a fleet of maybe dozens of hosts, right? Not hundreds, not thousands, but at least dozens of hosts, such that you don't want them to have pet names anymore. And we're also assuming that you're exporting some kind of metrics because you want to be able to debug your system. You want to be able to figure out what's going on inside of your system. But the problem is when you multiply all of this out, the number of hosts by the number of distinct metrics you're exporting, we're assuming that you're starting to struggle with complexity. That you're starting to struggle with how do I understand what's going on in each host in the system, and also understand what's going on at the top level of my entire distributed system. And finally, we assume that you have some degree of redundancy, that you have some degree of partitioning of your service, whether it's across availability zones or regions. And lastly, for the purpose of imagination, we're assuming that you're serving end-user requests because batch workloads are a completely different problem that requires different sets of techniques to solve. So let's assume that your system is merrily running along, and then something breaks. How do we find out? Well, some people wind up saying, we want to just monitor everything in the instant. Anything blips anywhere, that's going to hate us. That's going to cause us problems because you're going to be noisy all the time. So we're assuming that you've realized that things get really noisy really fast, and instead you're focusing on user pain. That you have a service level indicator that says users are seeing errors at too high of a rate, and that you have some kind of service level objective or error budget that says, here's how long we're allowed to be down, and if we start looking like we're going to be down or browning out too much, then we need to go and page someone. So we get paged, now what? We need to prioritize mitigating and root causing as quickly as we can, in that order. So I want to quickly go through this kind of way that we model people's response. Some of you may have seen it in the form of an OODA loop, observe, orient, decide, act. But this is kind of our formulation of it. So you're meeting your SLO, something breaks, and then you get paged. So what do? Well, first we have to do the blast radius, right? Are we having the global outage? Do I need to bring more people into instant response right now? Do I need to drain a region right now in order to stop the bleeding? But after that, there's kind of this critical loop that happens of we need to formulate a hypothesis. A lot of people get bogged down here and say, I'm going to look at my list of 50 dashboards and see whether I can figure out what broke. Which of these one squiggly lines changes at the same time as this other squiggly line? So we formulate a hypothesis, and then we do some experiments. We test and figure out, is this actually the thing that broke us? And then we develop a fix, and then we test, did our fix actually work in production? And if you're lucky, everything goes back to working as normal, you're within SLO. But the problem is, sometimes you're wrong. Sometimes your fix doesn't work, or sometimes your hypothesis is completely wrong, and the thing you thought was wrong actually isn't the problem in your system, and that you're chasing a ghost rather than the real problem. So we think that it's important to focus on how do you reduce that time of hypothesis formulation and testing to get your outages resolved faster and root cause faster. So we're going to work a real example that has 3 key techniques that we're going to demonstrate for you. First of all is layer peeling. Second of all is doing arbitrary data joins. And finally is the concept of mashing together your distributed traces or high cardinality tags together with your distribution data. So those are the three techniques that we aim to demonstrate for you. And one important note about technologies here, yes, we're showing you for the first time a set of UI tooling and a set of back-end stuff that Google does internally. But a lot of this stuff is perfectly possible to do with with virtually any set of tooling out there, whether it's Grafana, whether it's Zipkin. You can do this with technology that's out there right now. So we'll make public implementations where possible, and if there are some gaps, we'll highlight what the gaps are, so maybe you'll feel inspired to work on kind of closing the gaps now that you see what's possible. And finally, because we do work on GCP, so Stackdriver does not completely implement some of these things. We have these gaps too, and we're hoping that by kind of priming people to think about how you can do debugging better, that when those features eventually land, that you'll be prepared to use them. So Adam, your pager goes off.
This is where I step in. So I'm an SRE, so I get paged about these things. On my machine, I might receive something roughly like this. It says, there are too many slow queries, and it looks like that's happening in US West 1. But that's really all I can tell at this point. I don't really have very much context. We could try and stuff a little bit of context into our actual notifications, but like Liz mentioned, there are so many things that could potentially be going wrong, and so many hosts that could be going wrong, it would be completely overwhelming. So the first thing that we do is think about how can we get to the bottom of the actual problem, because I know that my SLO is a problem. I know that there are too many queries which are happening slowly, but there could be a lot of reasons. Potentially, we have so many replicas running all over the world, some of them could be broken. We could have, say, 2 or 3 replicas in some zone somewhere which have just gotten slow for whatever reason. So our task is to find those replicas, to hunt them down and to fix them. But alternatively, once we drill into this, we might find that the problem is just distributed everywhere. And it isn't necessarily one of our machines or one of our replicas that's the problem. It's, say, one of our users, which is a problem, or one of our configurations, which is the problem, or a shard, which is the problem, in which case we're going to have to diagnose what that problem is and get to the bottom of it such that we can resolve it. It's not going to be as simple as just tracking down a broken machine. So the technique which I'm going to use to solve the first problem, we call layer peeling. We tried to come up with a better name, but we just don't have one.
It's actually Tom's invention.
Oh, is it?
Yeah, Tom suggested it to us in the talk rehearsal.
Okay, well, it was better than nothing, which is what we started with. We're thinking about onions, you know? We're starting at the outside and we're getting to the middle of them. So the example I'm going to give here is, you saw we were paged because one of our SLOs was in danger. And our SLOs for this imaginary service are regional. So for some reason, US West 1, as we saw, is serving too many slow queries. We're going to drill down into zones after that. And we don't have any zonal queries. I mean, just to clarify the nomenclature, most of you are probably familiar already, but most of our services run at like a regional level, which is a very big, like a data center. And within those data centers, we have zones or availability zones. And within those zones, of course, we have machines and VMs and containers and blah, blah, blah. Now, we don't have a zonal SLO. So if one of our zones is completely broken, we don't get paid about it because, frankly, we don't care. Because we have redundancy in those regions. So ideally, if one of the zones is broken, our load balancers will shift the traffic. So I didn't receive a page that said US West 1C is broken. All I know is that US West 1 is broken. So first we're going to drill down into the zone. Secondly, once we've found the zone, we're going to hope, this is our hypothesis, we're going to hope that we can find some broken machines in that zone, but that means we're going to need to drill down to the individual machine level inside of that zone. Now, the reason we can't just say, let's look at every single machine or every single VM in the world right now is that would just be a huge jumble of lines. The cardinality is far too high that we couldn't possibly pick out one broken machine in a cluster of 5,000 of them. So this drilling down is going to be the key. So to start, if I were to click that link I received in my page, I would be taken here. This is Panopticon, or Peacon. And to be totally clear, this is an internal Google system, which we currently have no plans to open source, and we're not planning to expose it in GCP either. So you might be wondering, why am I showing you Peacon? There's nothing magical about Peacon. It's just, it happens to be the tool that we use. A lot of these techniques, as Liz said, could really be implemented on essentially any tool. It might not be quite as elegant, because if I haven't made it clear enough, I love Peacon. And previously, I didn't have access to this caliber of tools, but I could have cobbled together the tools that I did have to use this workflow. So Python is merely an example here. So we can see on this chart that whatever metric, which happens to be the latency SLI at 98th percentile, is being pushed up, and it crossed a threshold at some point. And we can assume that this is probably when I got paged. So the first thing that I'm going to do to solve this problem is pop open the query panel. Now, this metric, it doesn't exist in isolation. It's not just a number which is output by some opaque system which is being measured. It's actually, it's evaluated behind the scenes using this query interface. Now, I don't know how much you can read here, and honestly, it's not, the exact details aren't tremendously important, but there's a filter at the top of this which says metric region is US West 1. That's why I'm seeing one of these regions rather than all of these regions. And it's important to note at this point, it's a slight digression, but this is all graphical, what I'm doing here. I'm clicking because I'm debugging in real time, but all of this stuff is provisioned using textual query language. We use config as code just like everybody else. So when we're making changes to our alerting, we don't go in here and click around, of course. We make some changes in text, we test them, and then we push them out into production. But when I'm debugging, again, this is where I'm going to be clicking around. So firstly, let's just remove the filter so I can see the same metrics for all of our regions. The reason I would do that is, as Liz mentioned, to establish the blast radius. That's the first thing that we do. Because it's possible that I got paged about US West 1, but actually all of our regions are broken. This just happens to be the first one, and I can look forward to more pages about this. So just to establish this is not a global outage, I've modified the query in Python, and now I'm looking at the latency SLI for all of our regions. Thankfully, everything else seems to be pretty fine. So we've established the blast radius is one region. Now, this would be a great time to drain that region. If we have a lever to pull to do that, shift all the traffic to US East 1 while we work it out, that would be great. But we're going to dig in deeper. So we're going back to US West 1. We're going to re-add that filter. So we're already disregarding a lot of data. We're disregarding 2/3 of the machines in the world already because we don't care about US East and US Central. And then what we're going to do is drill down into this query. And this is why we call it layer peeling, because right now we're existing at the outside layer, just the regional SLI. But if I click on drill down, what I can do is interactively replace this query in place with the query which was used to generate the data which I'm looking at summarized. Now, if we could see the timing info of this, which is a little bit irrelevant when I'm debugging, it takes a second or so to pull all this data from all over the world, we would see this is a little bit slower because I'm pulling all of this data in real time, at query time, while I'm investigating. If we were to set our alerting on all of this, so every single time we wanted to check everything worked, we had to talk to every single machine in the world, that would of course be prohibitively slow for alerting. So we don't do that. We build up these progressive layers.
It's got two benefits, right? The first benefit is that it runs faster. The second benefit is that it's abstraction. It says, here's a boundary at which you can stop thinking about the query and just look at what's downstream of it. And then if you're interested in digging in deeper, you can dig in deeper and expand it. That's all this is.
Yeah, absolutely.
So what I've done here is, this step is a little complex, but I've gone from the regional view, taking this query, which essentially, again, you don't really need to read every single step, but essentially what it does is fetches the latency SLI for each zone as a distribution, and then it kind of adds them together. It mashes them together to make a regional SLI. So rather than doing that, I can actually drill into the query and I can group it by zone. Instead of grouping it by region, I can say, no, I want to look at the distributions of each of these different zones. So that's what I've done here. And you can see if I pop open the sidebar, which I've hidden for most of this presentation because this chart is already small enough in the middle of the screen there. But you can see one of our zones has much higher latency than any of the other zones. So we've gone now from the region, which we know is broken, now we know the zone is broken. So we can add another filter to this query interactively, where now I've filtered it, and now I'm looking at the latency for one zone, which is US West 1B. I'm going to refer to it as B from now on. Similarly, to the previous step, if we hadn't already drained the region, this would be a great time to drain the zone, because we now know that out of 5,000 machines around the world, we've zeroed in and know that the problem is somewhere it's isolated to US West 1B. So we're going to move forward and see what else can we find out about US West 1B. The very last operation here is a transformation. You can see the type the type of data which is going into this last stage is a distribution. That's a distribution of latency for all of the replicas in US West 1B. And then we're transforming it into a percentile, into one number to say, we don't care about most of this distribution, but I want to measure the 98th percentile latency because we can't very well make an alert that says, if the distribution looks kind of like that, then send me an alert. All we can say is, if latency at 98 or something like this, if latency at 98 is above 100 milliseconds, then send me an alert. That's what I want to receive. But when I'm debugging, I want a little more context than that because it's so hard to tell what's wrong from this. So I can interactively remove this last step. And now the query is going to be the entire distribution, because of course we're not limited to just plotting lines. We can plot distributions as heat maps on here as well. And I've done this enough times. It was a little foreign to me at first, but it's almost like reading the matrix. By looking at this distribution, you can get a pretty good idea of what might be wrong. You can see these lines are, I think they're the 50th, 90th, 99th, and 99.9th. The very bottom line hasn't really moved at all. So I already know it's not that the whole zone's broken. It's not that every single query that goes into US West 1B just is taking forever, because most of them, honestly, are taking as long as they always have, which looks to be about 70 milliseconds. But at some point, the higher percentiles started rising. So I know that there's some problem which is affecting some subset of queries which are going in and out of US West 1B. Honestly, it would be great if all of the queries were slow, because then... Really? It would be great if all of the queries were broken, because that would mean US West 1B is broken, I can pull the lever, and then I can get out of there. But that's not the case. So we're going to drill in even further. We're going to replace this definition with the raw data, which we're finally getting down to. We've bisected it successfully enough that we can now look at the distribution or the percentiles of the replicas in US West 1B, and we can see clearly one of them is broken. We've found that task. We've sort of solved the murder mystery. At least we've found the body at this point. So we're now adding another filter to say, filter only this one replica in US West 1B. I'm going to do the same as I did before and remove that 98th percentile filter. And now I'm looking at distribution of requests on this one replica. So now we know that all of the requests, because unlike the previous distribution, the actual baseline has risen. Now we know all requests to this replica are much slower than they're supposed to be. So the mitigation here is just, we're going to kill that replica straight away. We're not even going to go any further. We're just going to kill it and hope everything goes back to normal. So this, and that's the end of the that first strategy layer peeling. This is a very simple outage, but still, because the cardinality is so high, because there are so many replicas involved, there's no way that we could possibly have said, show me the latency for all of them, and I'll find the dead one, or the problematic one, because there's just too many of them.
Or even have a pre-canned dashboard for each of these. There's no way you could have done that. We had to interactively drill down to find it.
Yeah, it's impossible. So what we had to do is like chop, chop, chop until we found the problem. But unfortunately, not all problems can be solved that way. I'm going to go a little quicker on this because we include a certain amount of data with every single metric. We call them tags. So we can find which zone or which region every single query is coming from, but we can't, for example, find out which kernel version is this machine which served this query on. We can't exactly find out like what is the time or what is the patch version. We couldn't include out every single metric. So what we need to do is pull in other metrics which we can correlate with those. So I'm going to start with a brand new query here in Pecan in a brand new tab. This is sort of the simplest case of a query where we're essentially pulling a metric called proc kernel version, which, as I mentioned, it pulls out the version of the kernel which is running on each of our machines. This has got nothing to do with latency. It's just reporting this every 5 seconds or so we can keep track of it. Now, you can see on the right there's a lot of information about each metric. There's the host name, there's the location, there's a username and all of that. And we can use these to join all of the data together. So what I've done here is I've grouped the metrics which are coming out by version. And this is the very magical thing about having all of this data as standard. We can now see that the majority of tasks are running one kernel version, almost 50 of them. And there are a few outliers in there. So my hypothesis is there's something about this which is causing the problem. One of these kernel versions might be causing this latency event. So I'm going to open up another tab And this is the query which I mentioned we weren't going to do initially. This is just the latency for all of our replicas all over the world. It's just a huge jumble of data. There's not a tremendous amount we can do with this. But if I were to join these queries together, and the most important part, which I probably should have highlighted on the left, is we've taken those two queries and you see there's one box at the bottom which has joined these streams together. Now, I won't get into details of how this happens, but essentially we're able to correlate one metric with another metric using the username, the job name, the location, the replica, and all of that. And I hope it's clear how we've now highlighted on the right that we've augmented that latency data with kernel version data. So if I skip straight to the conclusion, if we now group the latency by that version field or tag that we just added, we can see something really interesting, which is that one of these kernels is causing much higher latency than any of the other kernels on it. The others are pretty much where they were. If I pop up in the sidebar, I can see, indeed, we seem to have one old kernel which is causing a tremendous amount more latency than anyone else. So at this point, I've already drained the zone, of course, and I've solved the problem using layer peeling, but at this point, I can file a bug, I can send it to our devs and say, hey, some of these replicas are running an old kernel. Firstly, I don't know why, and secondly, it's causing a lot of latency, so can you please take a look at that and fix it? Now, I'm going to skip over this slide because I just said all of it and we're running out of time a little bit, but we have one more strategy which makes these look like.
So Adam just spent maybe 15 minutes trying to figure out what was going on by onion peeling, and remember, he had to do that for each hypothesis he was investigating, for whether it's kernel version or whether it's which rack you're running on or any number of different things. You have to spend a bunch of time poking around the data. So I'm going to introduce to you a technique that really makes your distributed tracing useful and makes your high cardinality fields actually useful in a way that you can pinpoint problems precisely. So the way that we do this is by dynamically sampling. So we sample for a given distribution bucket, kind of the time dimension in one axis, the value segmenting in another axis. We may choose to keep for each bucket a specific subset of tags associated with one query that happened to fall into that bucket, or a specific, for instance, zipkin or stack driver trace ID associated with that. So that when we go looking later, we can go and find in our graphing UI and go and say, show me an example of a query that had this latency at this time, and give me the exact machine it originated from, kernel version, you name it, it can find it. And that's really the key insight of Exemplars that makes debugging a snap. So I've shown here what happens when you ask it to plot by task ID and to show me examples for the task IDs. And it will show you a whole bunch of examples of latencies kind of in the middle, latencies that are increasing. And I can go in and I can hover my mouse over one of those little dots that's an individual sample that's been attached to a bucket. And then it will show me everything sharing that same collection of tags. So in this case, it's saying, hey, all of these things that have high latency, they're all coming from the same place. And not only that, I can go and click and find out, hey, wait a minute, these all are coming from task ID number 4, right? So I've reduced all of that kind of onion peeling down into 20 seconds of querying and clicking to figure out what is my hypothesis. It's probably a bad machine. Okay, which bad machine is it? Now I know I need to go and look at or restart task 4. Here's another one. This is actually real data. This is not something that we made up. So I'm going to have to be careful with the numbers that I cite. You'll notice we carefully clip the axes. So here's a real distribution, and one thing that you'll note is I want to highlight that the 99th percentile latency is like slowly creeping up, but if you didn't have the heat map, you wouldn't be able to see that there's a whole band of queries that are slow, and there are more of them as time is progressing, right? That's the thing that becomes invisible if you only have access to your percentile lines. It causes you to miss patterns that are especially critical. So not only that, but we can actually say, I want to see one of these slow queries that is at n units. So I click there, and it will say, here's a trace. Here is a distributed trace, like a zipkin trace. Our internal version is called Dapper. And it will give me a link right there to say, here's the latency, and here's a way to go and dig in and find out what actually happened for that one query. So if I click there, what happens? Well, I get a basic view that says, okay, you talked to this server and it took this long, but I can actually expand this all the way down and say, hey, wait a minute. it's trying to make a bunch of calls to write data, and it waits for the batch to land, and then it writes the entire batch at once. And for some reason, more queries are having to wait the pessimal amount of time and units before they are flushed to disk. And not only that, we can also see, in certain situations, we can even see like log annotations, like what log lines were written in the middle of the execution of the query. So this is tremendously powerful because that lets me dig from, hey, I have a bunch of stuff that's slow, to what specific example can I look at to formulate a hypothesis as to what's going wrong. So now that I've said, okay, it's probably an issue with log flushing, now I can go and look at my log flushing graphs. If I didn't have this, I'd be poking around at 50 different dashboards trying to figure out, is it log flushing? Is it that the disk layer itself is being slow? What's going on here? Why is it being slow? So what I want to tell you here is basically that if you keep your high cardinality tags and sample them, or if you keep traces and sample them, you're going to have a much better time. Because it'll let you pinpoint exact hosts and timestamps and even distributed trace executions that let you really debug and figure out what's going on. You still need to be able to onion peel in the end. You still need to be able to dynamically construct queries in order to validate these hypotheses, but I typically spend 10 or 15 minutes if I don't have a trace trying to figure out what went wrong. So hypothesis to test gets faster, and your outages get resolved faster. So as a note, both of these things independently exist kind of in the public market in terms of distributed tracing exists, distribution graphing exists. The people that are closest to publicly implementing this, I would say, are Honeycomb, but we're hoping that soon other people will be doing this as well, and this will be a common paradigm that all of us use in order to root cause things faster. And then, we can spend that error budget on much nicer things. We can spend that error budget on iterating faster, making our customers happier, or maybe increasing our SLOs. So it's important to have, once you're done, it's important to actually write down what did you do, how did you solve the problem, in case the same issue crops up later and you have to figure out what's going on. They can reuse your work, right? But for committing these things to durable long-term dashboards, we don't really recommend doing that unless something is happening over and over. But if something is happening over and over, maybe you should be doing the engineering half of your job and fixing it. So don't proliferate dashboards. Every dashboard you add has a cost in storage, has a cost in compute, and has a cost in your cognitive overhead. Because no two outages wind up being exactly identical, so chasing yesterday's problems isn't really going to help you. So build better tooling to fix tomorrow's problems. So in summary, if you think about the whole OODA loop, focusing on time to resolve is most important, focusing on time to hypothesize and test is important. And if you have ad hoc querying and if you have exemplars, you can do that a lot faster. And if you can't do these things, you're spending a lot of time spinning rather than actually fixing problems. So that's it. Thank you.